Video number 2. I got my phone issues sorted out here. Let's continue on. So what I was talking about was these conjugate acid-base pairs, just another way to view a acid-base reaction. So again, in every acid-base reaction, you have an acid and a base on one side and an acid and a base on the other. They just are always grouped in these pairs to kind of organize the reaction a little better. If you look at the reaction of acetic acid and its reaction and why it behaves as an acid, it's reacting with water. So water is acting as a base, just like it did with HCl. This is a weak acid, so we write an equilibrium, not a left to right arrow. This is only about 5% ionized, so very weak. 95% of it is in this form, 5% of it would be existing as its conjugate base, the acetate ion. So this again would donate its proton to the water becomes protonated, a hydronium ion. The acetic acid loses a proton to become the acetate ion. So the conjugate acid base, this is a conjugate acid base pair, this is the other conjugate acid base pair. Even water, this is a very important reaction. It looks kind of confusing maybe, but it's water reacting with itself. But this is really where the pH scale comes from, why it actually has a number of 0 to 14, the scale. It's because of this reaction. Water can act as an acid and a base at the same time. Some of the water molecules reacting as acids, some will act as bases. They will switch protons and become a hydronium and a hydroxide ion. Again, this would be a conjugate acid-base pair. This would be the other conjugate acid-base pair. So please, I'd like you to be able to identify at least what they are. If I give you an acid-base reaction, can you pick out a conjugate acid-base pair? I'm not exactly sure what the word conjugate means. I think it just means a pair of some sort, so we're not going to worry too much about that. But just can you recognize a conjugate acid-base pair? It's easy to remember it, is that they just differ by a proton. There's one pair, here's another pair, here's another pair, here's another pair, and here's another pair. They just differ by one H plus being present or absent. So now we have the basics of what acid bases, the theory of how we view them. Let's talk about how we measure this this pH. So this is going to take a fair amount of time. It might be helpful if you had a calculator, a scientific calculator. I got mine ready to go here. I want to show you how you can calculate these numbers that we're going to be throwing at you. Let me just make sure I got all my pages organized here correctly. I think I do. I may be jumping back and forth here between pages, so but I'll try to go as this will take a while. So anyway, the pH scale, as you saw earlier with pKa, that lowercase p means to take the negative logarithm. It's a mathematical instruction to take negative log. Notice I write the word log. That means it's base 10. So I'm going to give you a little bit of a review on what logarithms are in a little bit as well, in case you've forgotten what that is, or maybe you've never seen them before. But it helps to understand what a logarithm is, to understand what the pH scale is. So the pH scale helps us understand the relationship between proton concentration and hydroxide ion concentration, and how concentration affects the pH and vice versa. The pH and the concentration, the molarity of protons, they're two different ways to express the same thing. But they're inversely related because they are a logarithmic scale. So very important for you to remember that if the pH goes up from 0 to 10 or whatever, it means the proton concentration is decreasing. So it's getting more basic. If the pH is dropping, going from, let's say, 5 to 2, then that would be becoming more acidic, which means the proton concentration is going up. So try to remember that. They're inversely related. pH is a measure of the acidity or basicity of an aqueous solution. It's a log-based scale based on powers of 10. So here's the basic definition, minus log. Notice there's a negative sign there. That's needed because pH is written as a positive number. Since these concentrations of protons in these acid solutions are all small numbers generally, they're less than 1, there might be like 10 to the negative 2 or 10 to the negative 3. You got to remember that we're dealing with acids and bases that are relatively dilute. You can have concentrated acids and bases, but we're talking in all these examples, we're talking about relatively dilute solutions. So if you take the logarithm of a number that's less than 1, you get a negative number. So they have to take the opposite of a negative, put the negative sign in there so that the pH is a positive number. So how does the log math work? Remember, it's based on a power of 10. So I'm just going to give you some examples here, and then we're going to kind of backtrack in a little bit and show you how we got those numbers, what they mean. If you find this all relatively easy, good. Then you might not have to, you can maybe fast forward a little bit. But if you're finding this confusing, please watch this a few times and then read the book. Isn't really telling you too much. It's just kind of giving you these numbers without explaining where they come from. That's why I want to explain it to you here. So let's complete this chart. I've already kind of done it for you, but I'll show you how this works. So with a calculator here, I think you can see that. Yeah, I should be able to see that number in the lighting here. So let's say you have, we can write the hydrogen ion concentration in a few ways. As a fraction, as a decimal, in scientific notation, and then we can convert that to a logarithm and then a negative log, which is a pH. So here's how it works. We don't really write concentrations as 1/10, but 1 divided by 10, as you know, is 0.1. 1 divided by 100 is 0.01. 1 divided by 1,000 is 0.001. 1 divided by 10 million is 0.0000001. So the number of zeros in a number that's less than 1 is always going to be 1 less than the power. So 100 is power of 2, there's 1 0. 1,000 is 10 to the third power, 3, so there's 2 zeros. There's kind of a pattern there. So written in scientific notation, 0.1 would be 1 times 10 to the first. 0.01 written in scientific notation is 1 times 10 to the negative second. 0.001 is 10 to the negative third. And this number with 6 zeros and a 1 is written as 1 times 10 to the minus 7th. The logarithm of these numbers, when there's a 1 here, when it's just some power of 10 raised to a power, the logarithm is the power. That's what a logarithm means. It is this is the base 10 system. LOG means base 10. The 10 is the base. What power are you raising 10 to? That is the logarithm. Easy. You don't need a calculator to get the logarithm of a number when the number out front of the power of 10 is 1. You can just say it's this number, and I'll show you how that works. I'll just enter it in. 1 on my calculator. To enter this number in scientific notation, make sure you can do it on your calculator, is a 1 EE, and then I just put 1 negative, and I have a little, I wonder if you could see that I think you can see that on the video. And then if you just press LOG, I see a -1 in the display, and that's the logarithm. And if I take the opposite of that, I get a 1. So I'll do that one more time. 1 EE -1. I have to go 1 negative. I press log, I get that. The negative log of that is just +1. That's the pH of this solution. If the hydrogen ion concentration is 0.1, it's got a pH of 1. So notice these numbers will always be greater than 0. They will be a positive number. Log of 0.01, 0.01 entered in my calculator, which is the same thing as this. If I press LOG, you'll see a -2 in the display, which the opposite of -2 is +2. So that's why the pH of that is 2. And so on. 0.001, which is 1 divided by 1,000. I get 0.001. But written in scientific notation on my calculator, I go second, press that key. I get 1 with a -3 here. That's that number in my calculator. I press LOG. I get -3, which is 3. So all well and good, pretty straightforward. The lower the pH, the higher the proton concentration, the more acidic. So that's a little bit confusing. It means that here's our pH scale. It goes from 0 to 14, and so numbers that are close to 0, between 0 and 7 are acidic. So that would be anything that has a concentration greater than 10 to the -7th. So all these examples I have in this chart are acidic solutions. That's why you see the pH is all less than 7. 7 is pure water. The pH of pure water, distilled water, is 7. It doesn't have, what it really means is that the number of protons in the solution is exactly equal to the number of hydroxide ions, the OH ions. It's a balance between those two things. So here's a pH scale. Battery acid, hydrochloric acid in your stomach, very acidic solutions. You can actually have negative pHs, but that's if you have a very concentrated acid, like concentrated nitric acid. You might have, if you remember in the lab, I showed you how I can dissolve a penny in nitric acid. Well, that nitric acid was so concentrated that it actually has a negative pH. All that really means is that the concentration of hydrogen ions in that bottle was extremely high, more than 1. As you go up the scale here, as you get less and less acidic, black coffee is a pH of 5, acid rain pH 4, pure water is 7, that would be distilled water. Seawater is slightly basic, pH 8. Now anything above 7 is considered a basic solution. Baking soda, ammonia solution, soapy water. Bleach is actually pretty basic stuff, the stuff we use to clean our clothes and kill mold. Drain cleaner like Drano, very, very basic. So as you get to the edges of this scale, they get more dangerous, so to speak. Very acidic, very basic, dangerous. Closer to the middle, more neutral, more safe to handle. Seawater, black coffee, things like that. So why is it 0 to 14? Well, I'm going to talk about that in a little bit. Where that number 14 comes from the reaction I showed you earlier, the water reacting with itself. So let's just go over some of the common numbers you'll see in a pH calculation. The pH of pure water is 7. That's exactly right in the middle. Right in between 0 and 14, halfway is 7. That's pure water. What's the concentration of protons in this solution? Well, it's just the negative log. It's actually the negative inverse log of that. So that, again, you'll need your calculator to figure that out. But this number is really the power, with the opposite of that number, negative 7, is the power to which 10 is raised. That's what I mean by a logarithmic scale. Pure water is neutral, meaning that there's not an excess of protons or hydroxides. They're exactly equal. It's neither acidic or basic. In order for pure water to be neutral, which it is, what does the concentration of hydroxide have to be? It's exactly equal to protons. So the hydrogen ions are equal to the hydroxide. That's pure water. And you'll notice that if you multiply those two numbers together, if I take 1 to the negative 7th power and multiply it by 1 to the negative 7th power, I get 1 to the negative 14th power, 10 to the negative 14th. That's where that number 14 comes from on the pH scale. It's because the particular equilibrium constant of water is equal to that number. It comes from it's called the autoionization of water. Water undergoes this very special reaction, this self-ionization, because water is very unique. It can act as an acid and a base at the same time. It reacts with itself. So this is acting as the base. It's accepting a proton, so it's becoming the conjugate acid of this is the hydronium ion, spelled this way. This red water molecule is acting as an acid. It's donating a proton to this water, and it's becoming a conjugate base, hydroxide ion. The concentration of a solution that has a pH of 1 is 0.1, and the concentration of protons in a solution that has a pH 2 is 0.01. So you see, as the pH unit changes by 1, the concentration of the protons changes by a factor of 10. That's like the, you might have heard of the Richter scale, which is, I believe, used to measure earthquake strength. That's a logarithmic scale. They use logarithms in measuring sound. The loudness of sound is the decibel scale. That's a logarithmic scale as well. Why did we do that? I think the reason why we do that is because people like to see numbers that are easy to read, like 1, 5, 10, whatever. instead of saying the concentration is 0.01, a lot of people don't really know can't relate to that, but they can relate to the number 2. So we convert that to a pH of 2 by defining pH as the negative logarithm of that number. So this is important to understand. A change in 1 pH unit reflects a 10-fold change in the concentration. So again, if you go from pH of 1 to 2, that is the difference between these two numbers. 0.1 divided by 0.01 is the number 10. I should get it in a different mode. 0.1 divided by 0.01 is, of course, 10. So that's what I mean by delta pH. The number is only changing by 1, but it's really a 10-fold change. A change of 2 units reflects a 100-fold change in the pH scale. So for instance, if you go from 0.1 to 0.001, if you take 0.1 and divide it by 100, you get 0.001. Well, the pH of this solution, 0.1 logarithm, that's a pH of 1. The pH of a 0.001 solution is the negative logarithm, 3. So that's a pH of 1, pH of 3. That's a difference of 2. So the change in the pH was 2. That's all. Like I said in the other video, you don't really need a calculator to do that. You're just looking at the powers of 10 when the power of 10 is written with a number of 1 in front. But the real world doesn't work that way. You don't always get nice round numbers for concentrations. So for instance, how did I fill out this table? Why is a pH of 1.60 equal to 0.025 and 4.07 equal to this, etc.? How do we do that? Well, let's just say, for instance, I was given that the pH is 1.6. How do I go from pH to hydrogen ion concentration? What I have to do, because of the way this is defined, I have to take the negative, what's called the inverse logarithm of the opposite of that number. Okay, that is confusing, I understand. I'm going to give you some examples and write it out. Maybe I should just do that here. I'm sure some of you are like, what's he talking about? So if you have a pH of 1.60, okay, how do you convert that to the hydrogen ion concentration? How do you do that? Well, just go to the definition of what pH is. pH is defined as the negative logarithm of the hydrogen ion concentration. So if you know the pH, let's just plug that in to here. So you'd have 1.60 equals negative logarithm of H plus. All right, we're trying to solve for the hydrogen ion concentration. Let's move the negative sign over to there. So you'd have a negative, all I did was move it over to here. And now I have the logarithm of H plus. This is just math, right? I'm just trying to isolate this by itself. So how do I get rid of a logarithm? Well, I take what's called the inverse log. So whatever I do, if I take the inverse log of a logarithm, it essentially cancels it out. But I have to do the same to the other side because it's an equation. I have to balance it. So if I take the inverse, I'll just write it as INV log. That's a mathematical term to say raise something to the power of 10. If I do that to this side, I can maintain the equation as long as I do it to this side. So the inverse log of a logarithm, okay, they cancel out. So I'm left with the hydrogen ion concentration here is equal to this number, the inverse log of this. Well, how do you do that on a calculator? Another way to write that would be 10 to the negative 1.60 power. So that's on this calculator, on my particular calculator, that's the second function of this here, you'll see is 10 to the x power. That's the second function of the logarithm key. That's what I'm talking about here when I write the notation like this. So don't panic, don't worry, you'll get this, it's not that bad. So all I'm doing is taking the pH value, plugging it into my calculator, 1.6, I don't really need to put the 0 in, and then I'm taking the opposite. I'm expressing it as a negative, so typing it as a negative, and then I press on my calculator second log, and this number pops up with a bunch of digits, but it's essentially saying H plus is equal to 0. What does it say there? 0.025. That's good enough. 2 sig figs in this point. So that's the molarity of that. That's where that number comes from here, 0.025. How do you check yourself? And notice how I wrote that here. It's to go from here to here, I raise 10 to the opposite of that number. So, and you can go, the other way is a little bit easier. Let me just show you that here again. You might want to pause the video just to see. I'll do that one more time with my calculator. So let me say, how do I go from here to there? I enter in my calculator 1.60, and then I take the negative of it, and then I take second logarithm, and I get that number, and I have to round it off. Since there's 2 decimal places here, then I only have to have 2 sig figs in my number. That's what that means. Same thing here. Let me show you how it works. 4.07. If I want to convert that to this number, let's say you were trying to figure out what the hydrogen ion concentration is, you would say, you'd enter that in, take the opposite of it, enter it as negative 4.07, and take the inverse log, which on my calculator again is that one. And notice I get this number. It's a very small number, so I'll just convert it to scientific notation. 8.5 times 10 to the minus 5th, which is what I wrote here. And you can always check your work. Now again, I can't stress this enough. This number is written, I have to round it off to 8.5, throw out all those other digits here, because this number here only has 2 decimal places. And I'll show you on the last one. Is that lighting allowing you to see that? Let me make sure I moved it a little closer. I think it is okay. Okay, so 11.10. Take the opposite of it, second log. There I go, 7.9 times 10 to the negative 12th power. Now let's check our work. You can check to make sure you did it right by going in the opposite direction, which is easier. You just take, in this case, I'd say 0.025. I'd press LOG and take the opposite of it. There we go, 1.60. And you cut off all those numbers here, because if this number only has 2 sig figs in it, I have to round this to 2 decimal places. 8.5 to the negative 5th. All you got to do to go from here to there is press LOG, not second LOG, just take the logarithm of that number. But remember, pH is the negative logarithm of that, so take the opposite of that, 4.07. 7.9 to the negative 12th power. I've entered in. Take the logarithm, you'll see, take the opposite of that, 11.10. So note again, 2 sig figs in the concentration of the protons means 2 decimal places in my pH value. So let's just stop and digest this for a minute. What does this mean? It means that a pH of less than 7 means it's acidic. A pH more than 7 means it's basic. Notice what that means with this actual concentration. Remember, the capital M means moles per liter. Something that's acidic is going to have a concentration of protons that is larger than this number. Notice those are all larger than 10 to the negative 7. So it might take you a little bit to figure. We're talking about very small numbers here. So if you prefer writing it out in decimal form with all the zeros, that's fine. But these numbers, this 0.025 and 8.5 to the negative 5th, are actually larger than this number. This pH of 11.10 is basic. That means the concentration of protons is going to be less than that number, and then you see it truly is. It's much smaller. It's 7.9 times 10 to the negative 12th power. So this isn't really discussed in your book. They kind of just give you these numbers in a chart. but I want you to be able to use your calculator for relatively simple calculations like this. If this is not simple at this point, stop and figure out how to use your calculator. You're going to need one that has an LOG, a scientific calculator, like you all have been bringing to class earlier in the semester, and learn how to use the inverse natural log, which again on my calculator, making sure you can see this in the video, on my calculator it will have a 10 with a x superscript. That is the inverse log, sometimes called the second log. So that's how I wrote it here. The INV inverse log is just raising it to the power of 10. And again, I'm going to give you a little bit of a review of what logarithms are in a little bit here, just to help those of you who are struggling with the math a little bit, or a little panicked at this point that you're not understanding what I'm talking about. I'm hoping you're all understanding what I'm talking about here. But the reason why, just to reiterate what I said, the reason why we do all this is because people like to see numbers like this. They can understand what a pH of 7 or a pH of 2 or a pH of 1.6 means. It means it's acidic. If I said the hydrogen ion concentration is 0.025 molar, that doesn't really mean anything to most people who don't have a scientific background. But they can understand what a number between 0 and 10 or 0 and 14 means. Lower means more acidic, higher means more basic. And getting back to this reaction here, the autoionization of water, let's talk about that a little bit more, and that will probably help you understand where I got those numbers from. So let's go back to this reaction again. It's going to be a little bit repetitive, I know, but these concepts, this mathematical stuff, sometimes you need to hear it a few times to fully get it in, to fully understand it. So here's our reaction of water with itself again, and it has a certain, it's an equilibrium because water is a very weak acid. How do we know that? Well, we can drink water, and it doesn't taste like an acid. Acids usually have a very acidic, sour taste to them, like vinegar. But water is an acid and a base at the same time. So, but the value, the amount of, the strength of the acid is extremely weak. But it's not so small that we can ignore it. We still have to take into account its acid strength. And that's this number here. It has this equilibrium constant we call subscript W because it's water, K sub W. So that's an equilibrium constant just like the equilibrium constants we've been talking about all along here. Ka, Keq, whatever. So Kw in this case, notice in this reaction, I didn't write it, but water is a pure liquid. These are aqueous, meaning they're dissolved ions. So in an equilibrium constant, as you know by now, you never put pure liquids or solids. The reason, again, is because pure liquids, concentration doesn't change. It's a very large number. We don't include it in an equilibrium expression. It's critical that you remember that. So this Kw, the equilibrium constant for this reaction, is simply going to be this concentration times that concentration. That's why I wrote it like this. You can also write it in a little simpler way. We can, instead of writing H3O+, we can write H hydrogen ions. This means exactly the same thing as that. I can't stress that enough. These are the same statement. This is just a little bit more detailed in that it's including the other water molecule. H+ is just a shorthand way to write a water molecule with an extra proton. You can't have protons floating around in water. They're much too reactive. So they exist, they really exist as water molecules with the extra proton, which we call this hydronium ion. It's drawn like that. But when they measured it, they were actually able to measure that. They took pure water many years ago. They were actually able to measure with electrical conductivity measurements. They were able to measure that these were equal in pure water, and they were both equal to 1.0 times 10 to the negative 7th. Kind of cool how that was kind of a round number to begin with. This is, I mean. But at 25 degrees, they measured those numbers, and then they said, well, if those are equal, the equilibrium number, the Kw, is just the product of that number. It's that times itself because they're equal. That times that, which is this times this. So if you square, if you take 1 to the negative 7th power and multiply it by itself, you get 1 to the negative 14th power. Okay, and that's where I got that Kw from. So that number, that going back a little bit, the 1 to the negative 7th power is just how many protons and hydroxide ions are in a sample of pure water. Very, very low number. It's it's really 2 out of every 10 million molecules of water are ionized. That's really almost nothing, but it's actually something we can measure. We have instruments that can measure that very low number. But that's what that number means. Only 2 out of every 10 million water molecules is actually ionized into these things. But there's a very important relationship between the proton concentration and the hydroxide ion concentration in water. They always multiply to give you that number. That's the nice thing about it. If you know the proton concentration in a solution, you can automatically calculate the hydroxide ion concentration because they both multiply to this number. So I'm at 31 minutes in this video, video number 2. I'm going to stop this now and continue on in video number 3, and we'll continue on with this discussion of pH.